All right, today's the last day of new content in relation to factoring, and the next class you guys will just have factoring day. Today we're going to talk about kind of some special products. We talked about these when we were talking about multiplying binomials going forward, and we talked a little bit about that it wasn't as important to specify or see the special case going forwards, but moving backwards it's going to be a little bit more crucial. So there's two of them we're going to look at today. Again, the first one is very, very specific. We want to be able to identify. The second one, you really could factor using methods we've already looked at. So this first one's called a difference of squares. Now, the difference of squares relates to exactly what it sounds like. The first of all, difference. Difference means subtraction, right? Really, really, really important that we understand difference of squares is going to be the subtraction of squares. So when we say squares, we're talking about perfect square numbers, okay? Now, we know what those perfect square numbers are when we see them, is the hope. But a perfect square, right, is when we take a number, an integer, and we square it, it's the number that comes out. So 1 is a perfect square because 1 squared equals 1. 16 is a perfect square because 4 squared is 16. All of these, right, 1, 4, 9, 16, 25, 36, 49, 64, all of these are perfect square numbers. So when we say a difference of squares, we're saying a difference of like two of these numbers. Or it could be a variable squared, like x squared. Now we could add a few more on here. Sometimes we'll see a little bit higher ones. So 13 squared is 169, 14 squared is 196, and 15 squared is 225. We could go a few further. But essentially, it's just really important that we are very familiar with these perfect squares. So when we return to class, we'll practice a lot with identifying perfect square numbers going forwards and backwards. Okay, once we find a difference of squares, now the reason we can factor it, notice down here, these are like the difference of squares. Okay, so when we talked about multiplying binomials, we said the only time you end up with a binomial after multiplying the two binomials is when we had identical binomials with opposite signs. Right? Every time that happened and we FOILed it, we got x times x is x squared, x times 5, negative 5x, 5 times x, 5x, 5 times negative 5, negative 25. Those middle terms were always exactly opposite, so they canceled out or added to 0, leaving x squared minus 25, a binomial. And notice it does the same thing on all of these ones. When we FOIL those middle terms, you have one positive 24x, one negative 24x that cancel out. So our goal today is to look at a binomial and recognize when it's a difference of squares and then be able to split it up. So notice if it's 64x squared, I know that the square root of 64 is 8 and the square root of n squared is n. So it's 8n and 8n gets to go at the beginning of each factor. And then we look at the 9 and we get a positive 3 and a negative 3 that would give us that negative 9. So it's essentially just splitting that up. So difference of squares, again, the rule is right here. If you notice that they're perfect squares, you just take the square root of the first and it goes at the beginning of each factor. The square root of the second is there at the end. Okay, and here's the steps. Again, number 1 is always factor out a greatest common factor if you can. Always, 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 even in identifying perfect squares. Then make sure it's subtraction. You'll notice all the examples 1 through 7 down here are subtraction, so we're good. And step number 3, again, the square root of the first term becomes the first term in each factor, and the square root of the second term is the second term in each factor. And then again, make sure they have different signs, one positive, one negative. So let's go through a few of these examples. I'm going to work through 1 through 4. Then I would pause the video, give a try to 5, 6, and 7. And then I'll work through those ones quickly so you can also check your answers there. So number 1, we've got x squared minus 25. Notice that's a difference of squares, right? This is one we kind of looked at above. X squared has a square root of x and x, so we know that's going to be there. 25 breaks down to a 5 and a negative 5. So we're going to put 5 in here, right, and negative 5, and we use that idea of the square roots, and it's already factored. Number 2, again, we look at it. Is there a greatest common factor? No, nothing divides out of 4. Z squared that also divides out of that negative 1. So we go ahead and we recognize that is a difference of squares. The square root of 4z squared is 2z times 2z. And the square root of 1 is 1. And then we need one positive and one negative. Number 3, again, this is not in standard form, but sometimes the difference of squares is written backwards, and that's totally fine because we're just using the square roots of each piece anyway. So the square root of 49 is 7. Square root of 16h squared, right, is 4h. We want 1 positive and 1 negative. Number 4, is there a greatest common factor? On this one, there is. So we look at this and we say, well, 50 divides by 2, 8 divides by 2. Those aren't perfect squares to start with, so we have to factor something out here. If they were perfect squares, though, we still would want to factor something out, or you'd have to factor it out at the end. So here it looks like we can divide both of these by 2. Now remember, the 2 doesn't disappear, it's coming out front. 50 divided by 2 is 25x squared. Negative 8 divided by 2 is negative 4. Now notice that 25 and 4, those are perfect square numbers, so we just split those up. So 25x squared, its square root is 5x. And the square root of 4 is 2. We need 1 positive factor and 1 negative factor. Again, maybe pause the video, try the next 3. I'm going to work through them really quickly, though, so you can check your answers. So you're just using those square roots of each piece. These ones don't have greatest common factors, so we're just splitting them up. Number 7, this one, those aren't perfect squares. Greatest common factor looks like it's 2, so again, you're pulling that 2 out, giving you 9x squared. Oops, so I almost put plus, minus 49, so there's a difference of squares. So we're going to have 3x and 3x from the 9x squared, and a 7 and a 7 from the 49, and then make sure those signs are opposites. Awesome, that's the first one. The second one is called the perfect square trinomial. We'll use this one a lot more in the future. But again, this one, you're given a trinomial, and if you're going backwards trying to factor it, really you can just factor it like we've been practicing normally. Just know that once it's written in 2x minus 3, 2x minus 3, we often write our final answer as 2x minus 3 squared. So it just means, right, that there's 2 of them. Again, we practice this going forward, taking this and writing it out twice so that we made sure that we multiplied correctly. And one thing we noticed is that the front piece, right, was always just squared. The back piece was squared. And then the x times 5 is 5x, and it was just doubled and put in the middle. So on this one, 2x became 4x squared, the negative 3 became a positive 9, and then 2x times negative 3 is negative 6x, and when we doubled that, again, we get that middle term. So that's what you're seeing over here, is that if you ever see a square root at the beginning, a perfect square at the beginning, a perfect square at the end, if those square roots, a times b, gives you the middle, then you know that this is going to end up being something like a binomial squared. And again, you could just factor it like normal. You would end up getting like a plus b and a plus b, and then just know that you can write that final answer as a squared term. Again, if there's a negative involved, this one would be a minus b, or in other words, a minus b squared. So as you look down here, let's look at these examples. We've got n squared plus 8n plus 16. Notice this is a perfect square. 16 is a perfect square. And the square root of this one is, right, n. The square root of this one's 4. N times 4 is 4n. And if we double that, we do get the 8n. So when we break this one up, that's kind of the shortcut. We could know, because of that pattern, that this would be n plus 4. So those pieces that you see there, squared. Again, if all else fails, just factor it like normal. Number 7, again, look for a greatest common factor here. It looks like a 9 can divide out of all of these. So if we divide out a 9, we get z squared plus 4z plus 4. Again, notice you've got a perfect square here, z squared. 4 is a perfect square. The square root of z squared is z. The square root of 4 is 2. So if I did 2z and I doubled it, I do get that 4z in the middle. So we know that this one could be 9z plus 2 squared. Okay. Again, these bottom ones I'll just show you. So like d minus 10d, d squared minus 10d plus 25. Again, if you didn't recognize the pattern, this would be just like any other one that you were factoring. You'd split up the d squared as d and d, and you would say what factors of 25 give me a negative 10. Well, they're both going to have to be negative factors, and it looks like negative 5 and negative 5 will work. You would end up with this, and then if you wanted to write it in perfect square form, you would say I just have two of the same thing. Okay. Again, looking at number 9, you could do that same thing that we've been practicing with factoring if you just recognize 2x and 2x and 3 and 3. And then you can notice, right, that if we look at this, that would give me negative 6 and negative 6. So essentially, again, you have 2x minus 3 and 2x minus 3. So when we do 2x minus 3 quantity squared, we can write it that way. Again, this is actually not wrong. So if you left it in that form, that's perfectly fine. We're going to practice writing it in the other form when we practice solving. All right, really quickly, you've got an application problem here. This one just relates to one of these special case functions. So this is talking about a bird picking up a golf ball. It flies up in the air and then it drops it while flying. And this function, y is equal to 81 minus 16t squared, represents the height y in feet of the golf ball t seconds after the bird drops it. And then the ball hits the top of a 32-foot pine tree. How many seconds does the ball hit the tree? Sorry, I read that wrong. So again, it's just important that we understand what everything represents. So this represents height, right, in feet, and t represents time in seconds. So when it asks me to find after how many seconds, when I'm making my plan, I know that I'm going to be solving for t, and that's really important to understand what we're solving for. And then what other information does it want me to figure out? It says, does it hit the tree? And the tree is 32 feet tall, so y represents feet. So when y is 32, we can solve for t. So if I let 32 be y, I get 81 minus 16t squared, that's equal to 32. This then becomes solving problem. So remember, we always want to set it equal to 0 first. So we subtract the 32 over, and we could leave 0 on the left side, and we get 49 minus 16t squared. Now, again, looking at this one, it's a difference of squares. So we can identify and use that tool now that we've learned to factor this guy out. So the square root of 49 is 7, square root of 16t squared is 4t, and 4t. And then we know that they need to be opposite signs. With quadratics, it's very common to get your two solutions and only one of them satisfies. So notice here, if I were to say what value of t makes this 0, well, that's a negative 7 over 4. And this one is a positive 7 over 4. So if we're talking that t represents time, that negative solution isn't actually valid. So we know that the ball hits the tree, right, after 7/4 seconds, or in other words, 1.75 seconds. Okay. Looking at 2.8. So 2.8, there's not a section in your guided notes book related to it. So I'm going to teach it to you off of this, and then we're going to add in a sheet and just do a couple examples. First of all, I just want you to bring your attention to the flow chart. This has all of the parts that we've done thus far. So you'll notice here it says, whenever I'm going to factor, this is what I do first. I look for a greatest common factor, no matter what. I don't care what it looks like, if it's a little binomial, if it's a trinomial, we always look for a greatest common factor. Sometimes that's all you can do. So you'll notice that this binomial over here, 3x squared plus 6x, all you can do is take out 3x, and now you have little linear factors. You can't do anything more in that case. However, sometimes you take out the 4, and then you have a trinomial that you could go further and you could continue to factor. So if you can continue to factor, that's where these arrows head, right? So first of all, we just talked about a difference of squares. Is it a difference of squares? If it is, there's an example there, right? 64x squared, there's the bells, minus 121. We take the square root of 64x squared, 8x. Square root of 121 is 11. And we can create our difference of squares there. There's even an example with higher powers of squares if you wanted to look at one of those. So that's one option. Now we know. We'll look for a difference of squares. If it's ever a binomial, check that out. Is it a quadratic, right, with a leading coefficient of 1? We practiced those a lot. We just need to break it apart. So we get x and x, then we get 3 and 5, and we just have to be careful with the signs. So those are just different examples related to the signs. If the coefficient is greater than 1, the method I put on here is actually the method that we did in the regular Math 2 class. If you're still struggling with factoring when the coefficient's greater than 1, feel free to use this method, and I attached that video to the last lesson. So otherwise, we just talked about taking this, right, and looking at 5x and x. We look at all the factors of this, 2 and 6, 3 and 4, 1 and 12, and then we figured out which factors would match to give us 19. And we just kind of went through and said, okay, well, what if I did x and the 4 over here? That gives me 4x. 5x and 3, that gives me 15x. Perfect, that gives me 19x. So then we wrote it out, 5x and x, and we used the 3 and the 4, and we just make sure they match to give us 15 plus 4x, 19x. So we always have those methods we can use. Again, this is just a reminder of the sign rules for factoring, right? If this is a positive sign and everything's positive, then your signs in your factors are all positive. If this guy's positive, but this one's negative, then these are all negative. And then again, if you ever have a negative at the end, you have one of each. Now, the only new piece that we haven't talked about is this on the left. This says, are there 4 non-like, then it paused, that should say terms. If there's 4 non-like terms, then we use what we call factor by grouping. Again, it's kind of like using a greatest common factor over and over again until you have your pieces together. So I'm going to show you an example here, and then we'll work out a few of them. This says, notice we have a cubed term, a squared term, a linear term, x term, and then just a constant. So we have 4 unlike terms. So the question is, how would I factor that down? Well, we group them. So if we grouped these first 2 and said, well, let's just look for a greatest common factor in these 2, notice that both of those can be divided by 3. They also have an x squared in common. So if we divided out a 3x squared from each of those, that's terrible writing there. A moment. So let's say we took this group right here and we factored out, again, a 3x squared from each of those. You'll notice that's what's happening here. They pulled the 3x squared out, and 6 divided by 3 leaves that 2, and then there's an x left. And then the 15x squared divided by 3x squared leaves that 5. So again, they just grouped those first 2 terms together and factored. Then we do the same with the second 2. So now 4x and 10, they get to be a group. Well, the only thing that divides out of both of them is a 2. So when we divide that 2 out front, right, we get 2x plus 5. Notice now you have a 2x plus 5 and a 2x plus 5. Because those are identical, that becomes a greatest common factor. It's just 2-term, it's a binomial common factor. So what we do is we almost factor out the 2x plus 5 and it comes out front, and then we put the leftover pieces in their own binomial. Because if you factor out a greatest common factor, right, you put what's left in your parentheses. You'll notice down here they did the same thing. They took out a greatest common factor of x squared in the first piece, greatest common factor of -4 in the second piece, leaving an x minus 3 as the common factor. So we get x minus 3 out front, and then we get rid of that, and x squared minus 4 gets to go here. Now when we factor completely, notice this is still a difference of squares, so we're not done yet. This guy can be split up. We go x and x, right, to split up the x squared, and the square root of 4 is 2 and 2, and then we have different signs. So this one, actually, this is its factored all the way down. Now notice that first example, there were no difference of squares here, so we didn't go any farther. Okay, I'm going to add in one page, and we're going to just do a couple more examples of that. So again, this is called factor by grouping, and we use this when we have 4 unlike terms and we want to try and factor those. So let's just do an example here. Let's say we have 10n cubed plus 6n squared plus 35n plus 21. So working through this, again, we're going to group them. So there's nothing common to all four. Now, if there was, we'd pull that out first. But again, we're just going to look at this first group. A common divisor of 10 and 6 would be 2. And then we've got n cubed and n squared. So n squared is the biggest common factor there. So again, I'm going to pull 2n squared out front. That leaves me with 5. I have n cubed divided by n squared is just n. And then 6n squared divided by that 2n would leave me with a 3. Once you have the first group done, you move to the next group. So 35n squared plus 21. Well, 35 and 21 are both divisible by 7. So I'm going to put that positive 7 out front. Then we look at what it would be if we do 35n divided by 7. Well, that's just 5n. 21 divided by 7 is a positive 3. Notice we have it right where we want it. We have 5n plus 3 and 5n plus 3. So the 5n plus 3 is pulled out front, so to speak, and then whatever's left goes into that second factor. So we've got our 2n squared at the front plus 7. Notice there's no difference of squares on this one, so we would finish off right there. Now, oftentimes if you have a negative involved, so let me show you another example here. 14x cubed plus 49x squared minus 10x minus 35. On this one, again, you're going to group them together, so there's nothing that divides out of 14 and 49 and 10 and 35, so we're just going to go here and say, well, 7x squared could divide out of here. So we divide 7x squared to the front. When we do that, we end up with 2x. 49 divided by 7 is 7. And then notice here, if you look at this one, the 10 is negative. And so I'm going to pull out a negative common factor. Whatever I pull out, just pull out a negative with it. So these look like they're just divisible by 5. So if I pull out a negative 5, that leaves me with negative 10x divided by negative 5 is 2x. And negative 35 divided by negative 5 is a positive 7. Now, if you didn't pull out that negative, you'd still have a negative in here. And hopefully you'd realize if these aren't identical, you need to go back and change the factor that you pull out. Okay? So again, notice that we have a 2x plus 7 and a 2x plus 7, so that gets to go first. It doesn't really matter if it goes first or second, but it gets to go in one of the factors. And then the other factor is the leftovers. So 7x squared minus 5. Okay, so you're going to try a few of these, see how it goes. Again, you can always refer back to the factoring flowchart if you ever get stuck while you're factoring. You're going to factor and practice a bunch of these, and then we will take a quiz before we get to our review and our final exam to make sure we're doing great with factoring.